So here I'm holding a pestle, which, if you're not familiar with what that is, it's basically a rock that gets used to grind spices. And most of the light that's hitting this pestle is diffuse light, or I should say that it's diffuse reflection that we're mostly seeing. However, as you can see, we also have highlights and very visible highlights along this as well. And so you might be wondering why it is that we have all of this diffuse reflection happening, and these highlights are also really intense at the same time. How does this make sense based on what we already know with diffuse reflection at the molecular level? And how can we take our understanding further by incorporating specular reflection? Well, let's take a look at that right now. The most useful way to think about specular reflection is in two parts. We have specular reflection that occurs at any surface points. And so this is generally referring to the likelihood that a specular reflection will occur along any object. And then we also have Fresnel. And Fresnel is specular reflection which occurs as you approach a grazing angle. So with all objects, as you approach the grazing angle of the object, you will see that light behaves more and more in a specular way. And we'll talk about why that is here in a little bit. But for right now, I want to talk about specular reflection that occurs at any angle, and it's just the general likelihood that light is going to behave in a specular way. So, to understand this, we have three things here. We have dielectrics, semiconductors, and metals. All things in the world are one of these three things. And the reason why that's important is because depending on what it is, a dielectric will have 2 to 8% of the light behave in a specular way. And this is most things in the world. So wood, glass, stone, skin, basically things that aren't metal are dielectrics. And usually this value is around 4% of the light behaving in a specular way. Next, we have semiconductors, and semiconductors exist between 8 and 40%, roughly speaking. However, the thing about semiconductors is that you rarely run into them. These usually belong to more exotic and rare materials such as crystalline silicone, germanium, diamonds, and so it's not very often that you're going to run into a semiconductor material. But just for your own knowledge, that is another type of thing that you can have. And then we also have metals. And so metals typically see 40% or more of the light being reflected in a specular way. And examples of that would be gold, steel, copper, platinum in their pure form. Oxidation is different, but in pure form, these metals have about that percent likelihood of light reflecting in a specular way. So with that being the case, let's take a look at metals since they have the most specular reflection out of any of these and talk about what's happening when light meets a metal. What makes the chemical properties of metal a lot different than dielectrics in this case is due to their electromagnetic properties. And what ends up happening is this. Metals create a bit of a shield that prevents light rays from going inside the medium and bouncing around. This is the primary feature that distinguishes metals versus dielectrics. It's why in dielectrics only 4 to 8% of that light is specular versus 40 or more percent in metals. So this electromagnetic radiation, it creates this barrier. And what ends up happening is this. If we have light that goes down, it's more likely to bounce up like that. And again, this is about 40% of the time lights will just bounce off cleanly like this. And for these rays right here, the light is being absorbed or attenuated, meaning that that light gets canceled out. Something I'll talk about in the future is this thing called the absorption coefficient. And the absorption coefficient is talking about how light gets attenuated or gets canceled out and killed as soon as it interacts with these metal atoms. For right now, just think about this as we have metals and we have dielectrics, and they're two separate things. Again, dielectrics don't have the shield, and because of that, that's why most of the light is able to go inside the medium, bounce around, and come out in a diffuse manner. Also, I should mention that part of what makes this around 40% of a specular reflection is just due to how densely packed these atoms are. As you can imagine, the more densely packed these atoms are, the more likely it is that light is going to hit one of these atoms and bounce off rather than be killed. And so we're going to get into IOR here, which is index of refraction, in a little bit, but just know in general that the more dense your atoms are, usually that correlates with a higher IOR value. And so as we'll see here shortly in Houdini, as you increase the IOR, you increase the amount of specular reflection as well. But anyway, I'll get more into that here in a minute. Let's talk about Fresnel. Now that we know all about dielectrics, metals, semiconductors, it's better to think of objects in these terms as opposed to what we had before with the red side and the blue side. So now we have this collection of atoms right here, and let's think of this as a dielectric. We don't have that nice fancy electromagnetic shield to protect this sphere from light. And so in other words, light is able to bounce around in a diffuse way within this object. Now, when we talk about Fresnel, we're talking about something that occurs when we look at this object at a grazing angle. In other words, as soon as we approach the top of the sphere and the angle at which we look at this, what we'll notice is that more of the light behaves in a specular way. And this is why that happens. If we just take a look at the individual atoms, what you'll notice is that at these grazing angles, the light is a lot more likely to just graze the atoms and bounce off, as opposed to finding some gaps, like a straight-on hit, like that, and then bounce around in a diffuse way. So I'll try to say that again because it's really important. These light rays, when they hit the sphere of atoms directly, they're more likely to bounce around and find opportunities to do so. But if we approach the grazing angle, those opportunities become less and less available. And that's why, as we approach the grazing angle, things appear to be more specular. This also accounts for why 4% of the light in a dielectric material is a specular behavior. That's because we still have atoms along the surface here, and sometimes the light will hit these atoms directly and bounce off. Like you can see this happen right here. But the remaining percentage of the time, the light is entering into the medium, bouncing around, behaving diffusely, or it's being absorbed. So that is why a dielectric sits at about 4%. And as we reach this grazing angle, we have near 100% chance of a specular reflection to occur. And the combination of this percentage right here, the direct hits, let's say, along with the Fresnel, accounts for the specularity on all objects. So now check this out. We have the pestle again, right? And if we take a look at the Fresnel right along here, what is causing the light to hit these particular atoms? We're looking at it pretty much straight on, and so really the light that's hitting these areas is reflecting off of the black shirt. But even though it's a black shirt, it's reflecting in a purely specular way, and because of that, we have these bright highlights. So that's Fresnel. Compare that reflection to the direct reflection that we see right around here. This reflection is coming from the bright light. It's facing towards the bright light, and yet that's not as visibly bright as the Fresnel. That's because only 4% of the light is being reflected back in a specular way. If this was a metal, and 40% of the light was reflecting back to our eyes in a specular way, then these highlights would be much brighter. So anyway, that's just a bit of real-life analysis of specular highlights, what's happening there on the atomic level, as well as what we can see here with real-life reference. Very shortly, we'll take all this information and use it to help us make accurate artistic choices. But before we get there, let's talk about roughness and absorption. There's a couple more pieces of information that need to come together before we can start looking at things in the real world and applying that to shader settings that we see within the principled shader.